This is by request by one of my geometry students, and I just got the email, so hopefully it's not going to be posted too late for y'all to get some help on this homework problem. And I intentionally left some things vague, and I probably ended up confusing a few more than a few students in class today because I was not really wanting to tell you how to do it. I alluded to a couple of ways. I'm going to show you one of the more simple inductive ways of doing it because the theme is inductive reasoning for the most part. So let's go ahead and get started. Now we're going to be looking for diagonals. It's going to be a little bit different than the handshake game that we did in class. So what we're going to do on diagonals is we're going to start off with a three-sided figure. So I'm going to do number of sides and vertices. Vertices are right here. I'm going to have three right here. This is my triangle. Okay, triangle. And I cannot make any diagonals. So the number of diagonals from one vertex right here, I just can't do it. So I'm going to have 0 diagonals, all right? And of course my total diagonals is also going to be 0. So let's go over to the square, and this is what we started off with a little bit to look at today. And I can take a diagonal here and go this way, and I can do a diagonal at B and go this way, okay? And if I was an individual like we had, I can have a diagonal go this way, and C can have a diagonal go this way. Now I'm double counting here, but I'm doing that on purpose to illustrate something. So here's my little square here. I have 4 sides, 4 vertices, okay? And I'm able to do from one vertex just 2 of these guys, and the total diagonals, all right? Now I told you about double counting, and we're going to come back to that here real soon, okay? Oops, total number. I'm sorry, I did that wrong. I need to put a 1 here. I'm doing things in my head. I have made all kinds of mental math mistakes today. Okay, so now we only have 1 from one vertex right here. Now we're going to do the pentagon. 1, 2, 3, 4, 5. Well, 5. And we have 5 of these vertices. Now from one vertex I can go here, I could go here, and I'm kind of bummed out. That's about as all I can do. But I have a lot more than that. I can go from this guy right here to here, and I can go from this guy over to here. And I can have lots of double counting going on for this. So I have a total of 5 diagonals. 1, 2, 3, 4, 5. Okay, do you see them? So I have 5 of these puppies. Boom. Now I'm going to go to my hexagon. 1, 2, 3, 4, 5, 6. Close enough for government work. So we got 6 right here. And I'm going to go from 1 vertices. 1, 2, 3. Okay, I'm going to put a 3 right here. But I can also go from this guy 3 more. So that's a total of 6. I'm counting in my head this time. And this guy is being left out. Okay. I already did that one, that one, that one, that one. So what do we have? I'm missing, I got 1, 2, 3, 4, 5, 6. Boy. This one. There we go. 1, 2, 3, 1, 2, 3, 1, 2, 3. I should have 9 total. Okay. Now, what I have is, let me scroll down. Come on, scroll down, let's send page. What I have here is a setup. We're going to have to look for a pattern, see a little bit of our inductive pattern. Now, number of sides, vertices, and number of diagonals, if I were to actually come up with multiplying for this, I would get an equation like this. Not a problem. But here's one of the problems I have. 4 times 1 does not equal to 2. So we're going to have to do something to this. We're going to have to do something to that. Now let's see what kind of pattern we have here. We have 5 times 2 definitely doesn't equal to 5. That could be a problem. And then 6 times 3 doesn't definitely equal to 9. Well, we have, of course, 18, 9, 10, 5. You know we're multiplying by 1/2 or dividing by 2, so we're multiplying by 1/2. Now, I have a polygon here, well, with a lot of sides. We'll call that n number of sides, okay? N number of vertices. And what we're doing here is, if you notice, we're down 3 on each one of these. So n times n minus 3. And we're going to multiply that by 1/2 is equal to the number of diagonals, and I'll call that d. And that's how we get our formula. D is equal to n times n minus 3 over 2, or 1/2, however you want to do it. And that's actually a quadratic, which I alluded to. And you can use the quadratic to even work backwards. Say you're given the number of vertices, you can solve the quadratic to do that. But we're not interested in that. We just want to know how many is interested in, and this is problem number 4. So we got to have, what did it ask for? How many diagonals? Well, let me look at the book. Oh, it's right there in front of me. See, I told you I'm very tired today. So we're going to plug in 35 right here. So 35 times 32 all over 2. Okay? So 16 times 35, whatever that is. Did I say 25, 35? Somebody help me. I am way too tired. 560. And voila, 560 is our total number of diagonals. Hey, write. I told you to write. I mean it. There we go. All right, I'm going to post this for the requested student. This is just one way to do it. Some of y'all found other ways. This is the inductive way. I kind of like it. I didn't show this to you on purpose, though, because I was kind of hoping that you would figure it out. So, but if you did another way, that's perfectly fine. I'm going to let y'all go and call it a night.